Hello everyone. In this video we will continue to examine topic 12.1, the interaction of matter with radiation, and in particular we will finish examining the photoelectric effect. Alright, in the last video we went through sort of the phenomena of the photoelectric effect and how the four surprising results acquired by considering the experiment could be explained. Those results can be measured, and there's a very important graph to really know your way around that came out of these results. And that is the graph of the maximum kinetic energy of the electron versus the frequency of the incoming light. Now, if we take a look at this graph, we'll zoom in on sort of one of the lines to begin with. What happens is that as you increase the frequency, the maximum kinetic energy of that light increases. And it's a linear increase, and the equation of this line is governed by sort of the fundamental physics underlying the energy of a particular electron. In particular, the maximum kinetic energy of that electron is equal to the incoming energy of the photon. So the energy of the photon that strikes the electron to begin with, minus the work function, otherwise known as the energy required to eject the electron. Another way of looking at it is that the kinetic energy of the electron, which is what the energy is of the electron that escapes, that is emitted, is just equal to the difference in the incoming energy and the energy required to literally escape the metal itself, the work function. Notice that the work function is equal to h times f naught, the threshold frequency. So the threshold frequency is just the minimum frequency with which one could eject an electron. And on our graph, right, that lies at the x-intercept, okay, the frequency intercept here. Notice that this equation is the equation of this line. This relationship is linear because the maximum kinetic energy is only dependent on the frequency and the work function of the metal. The work function depends on the metal, so notice that this line is completely independent of intensity. If you increase the intensity or decrease the intensity, it does not affect this line because the intensity simply increases the number of photons rather than the energy of each photon. Note that the red line here is in comparison to the green line, and the difference between the red line and the green line is that the red line has a low work function. That is, it does not take much energy for metal 1 to eject the electron, and therefore has a low threshold frequency. Likewise, for the green line, the metal has a much higher work function, or much more negative y-intercept here, and therefore a much higher threshold frequency. This is a hard-to-eject electron and an easy-to-eject electron. And notice that for both of them, the slope is h, or Planck's constant. This is literally how Planck's constant is measured. This experiment represents the discovery of the value of Planck's constant. Planck's constant is named after Planck because of his hypothesis in which he solved or proposed a solution to the ultraviolet catastrophe, which we have seen before. And in it, he said that the energy was quantized, but he did not have values. Planck's constant is where we get the value. Okay, it's the slope of this line. Notice that for this graph, you want to be very familiar with this graph and its relationship to this equation here. But there are alternative linearizations for this graph. So instead of seeing the maximum kinetic energy versus the frequency, you could see, for example, the stopping voltage versus 1 over the wavelength, or any combination of different things. They'll look the same, they'll have the same interpretation, but the values you read off those graphs might be slightly different, and you have to be ready for that. To find the equation of these lines, right, we can consider this fundamental relationship here and then divide by the elementary charge for every term. And if we do that, we get this result right here. Notice that I have also substituted in this particular equation for the frequency, substituting in f equals c over lambda for that frequency. And so this linear equation is the equation of this line, just with a bunch more constants in it. And notice it changes the y-intercepts as well. Those y-intercepts become the work function divided by E rather than the work function alone. And so you just have to be a little bit careful about what the graph is actually telling you and then respond appropriately, because there are other linearizations of this graph. Finally, in considering the kinetic energy versus the frequency, you should note that the values of the work functions, and indeed the values of the maximum kinetic energies, are very, very often given in electron volts. This would be perfectly fine and great, and we could all work in electron volts, except in the data booklet, Planck's constant is only given in joules, or joule seconds. And what that means is that in doing these problems, you need to get very comfortable converting into joules because these will be in joules when the values you're given will often be in electron volts in one form or another. So just be aware of that.